All right, we're pretty much wrapping up this chapter. We're going to spend a couple days on this topic where we've dealt with a lot of intersections, or we dealt with the intersection of two planes last class, and now we have to look at the case with three planes. So for this, again, if you've got a couple of things that you can use to pretend they're planes, that'll help. Just a couple extra pieces of paper or notebooks or binders or whatever. We have to try and think about the different ways that three planes could interact with each other. So the easiest one to picture, because you can do it just with the walls, is thinking of the XY, the YZ, and the XZ plane. So if you just look at the corner of the room you're in, you'll have three planes intersecting, right? All of those walls. And if you think about where they all meet, they're all coming to a single point, right? They're all meeting at one corner. So if you did the floor and the two walls, that bottom corner right on the floor is the intersection. And in that case, it's 1 point, right? That's all. Now what I want you to imagine is if we take one of those planes, just one of the planes, leave two of them right where they are, take one of the walls maybe, and imagine we could tip the wall and we could start moving it around in different directions. If we did that, the point of intersection is probably going to move, but it's still a point. You're still going to get a point of intersection in that case. However, it starts to get possible where you can arrange planes in just the right way so that we don't get a point of intersection. A point of intersection is the most common. So if I take any three random planes, they probably intersect in a point. But there's some other things that can happen too. So notice here it says, how might three distinct planes interact with each other? So I'm using the word distinct. There's of course the possibility that I give you three equations and all three planes are exactly the same. There's also the possibility where I give you three planes and two of them are the same and one's different. If all three were the same, that's very boring, right? It's really just one plane, there's an infinite number of intersections. If there's two planes that are the same and one plane that's different, then really you've got a situation that's just like what we did in the last lesson. It would be like having two different planes, right? Because two of them paired up anyway. So those are the not so exciting cases. We'll have to talk about them a little bit, but they're not as exciting. So things that might happen. Well, we might get a case like this. Like I said, with the walls and the floor. You might get a situation where all three planes intersect in a point. Or you might get this. So notice they're distinct. Right? I've got two parallel planes, and then the third plane slices through. So that would be like the floor, the ceiling, and a wall. Now if that happens, we ended up with two lines of intersection. Right? You can see, I can draw it on here. You have this line right here, and this line right here. But we'd say, is there a common intersection? Are there any points that actually touch all three planes at the same time? And there isn't. So technically with this one, there's no intersection. Okay, we have two parallel planes, so they intersect the third plane in two different lines, but there's no, I guess you could say, no overall intersection. Because when we're talking about an intersection, what I'm looking for is a point or group of points that would intersect at all three, has to touch all three. Or there's this guy. It would be possible to get all three planes to actually intersect all in one line. So this one has a line of intersection. And you can do that with your textbook, right? Just open it up so that there's three different sections for it. And once again, the spine becomes the intersection. So that has a line of intersection. That means we would need to find that line. So if we're in that situation, we'll need to be able to figure out what the equation of that line is. We'll have that today. We're going to try that. This one's kind of cool. It's similar to the one we just said there with the line of intersection, but what you'd imagine is take one of those planes and slide it out a little bit so that instead of being perfect and intersecting right along the same line, these are now intersecting in three lines. One there, and one there. This one's a little bit trickier because there's no parallel planes in it. So it won't be as obvious to us when we start, but we end up with three parallel lines, but there is no intersection again. So there's no common intersection. And the way we refer to this, we say they intersect in pairs. And the way that works with the pairs idea is if there's three planes, I can pick a pair of them, pick two planes, and find their intersection. And then I could pick a different pair and find their intersection. And then I could pick the final pair of planes and find their intersection. And all you'd be doing is you'd be finding all three of those lines. We will never have a question like that, okay? What I mean by that, you may have a question, and I think we're going to see it again today actually too, where this is the situation we're in, right, where we have no intersection because the planes intersect in pairs. What I won't ask you to do, I won't ask you to find all three of those lines. That would be a waste of your time, okay? So we're going to have situations where I'll give you equations, and it will be that picture that we see, but our conclusion will just be, oh, these ones don't intersect because they intersect in pairs instead. And here's our third really boring case. These are all distinct, right? None of those planes are the same. They're all parallel though. So that would be like floor, ceiling, second floor ceiling, I suppose. Three parallel planes, they never intersect. So the only ones that actually have an intersection are this one and this one. Those are the only two cases there where we'd be actually finding an intersection. Okay, you can take a look at this for a minute. We're not going to do too much here, but this is just how we start to recognize patterns out of the equations. It helps if we're going to do it every time. Before we do any algebra, we're just going to look at the equations themselves and see if we can tell if planes are parallel or not. So in this first case, you've got equation 1, equation 2, and equation 3. And I'm going to label that. It's going to help to call different things equations 1, 2, and 3. But what you'll notice is if I multiply the n value, right, let me put it down here, the normal vector from plane 1, if I multiply that by 2, that gives me the normal vector for the second plane. Notice the d value, the +4 and the -7, are different. So they aren't the same plane, only the normal vectors are multiples of each other, which is going to make those parallel. And similarly, 3 times n1 gives you n3. And this is also true. If I multiply 3 over 2 times n2, that gives me n3. That's not quite as important, but the fact that that also works. Part B there, it says pi 1 and pi 2 are coincident. Coincident is the word we can use to say that they're the same plane. They're right on top of each other. So that's looking at this one and this one. And you can see that what we've done is we just multiplied the whole thing by 4. So 4 times pi 1 equals pi 2. Oops, not 4 pi 2, equals pi 2. But then the third plane is parallel, right? You can see on that one, you've multiplied the normal vector by -1. So if I go negative, oops, it's supposed to be an n. The normal vector of the first plane times -1 gives you the normal vector of plane 3. And then final example there, part C, everything's just a multiple of each other. So you have all three planes exactly the same, okay? As I say, we're gonna look for that first. So when we're doing our examples in a second, we're gonna take a look at those equations right away. Here, if you have two planes that are parallel or not. So how would you know that? Well, you can see that these two guys are parallel, right? They're not the same plane because of the +4 and -7 again. And you know that the third plane is different. So if you see that situation, this is where we said, look, there is no common intersection. They intersect in lines. But we'll just say there is no intersection and you describe it. You'd say there's no intersection. We have two parallel planes, and the third intersects both. But at no time here are we actually trying to find that intersection. Part B, now you've got the first plane and the second plane that are exactly the same, which in a sense means you can just get rid of one, pretend it's not there at all, and now just think of it as a situation with two planes, and then you would do the question exactly the same as we did last class. Okay, so that situation won't be new to us. These ones are the ones that are new. And I mean, this slide has a whole bunch of equations here, but there's nothing to notice from these equations. Okay, you can't see anything out of them. None of the normal vectors are multiples of each other. None of the planes are multiples of each other. So there's nothing to see, except to say that we're going to look at them and go, oh, look, there aren't any that are multiples of each other. At least that means there are no parallel planes. Okay? Keep in mind with part A, there's no solution there. We say they intersect in pairs. Part B, there is an intersection. They intersect in a line, in which case we'll have to find the equation of that line. And part C, they're intersecting at a point, which means we're going to have to find the coordinates of that point. This is another neat little part. We're not going to deal with this one too much, but it's worth noticing. And this may be tricky for you to picture, but if you flip back through those slides, if you just back up the video a little bit, it says that notice in all cases except when the three planes intersect at a single point. So every case except this one here, the normal vectors would all be coplanar. And I'm not sure if I can show you that too. I'm going to try to on here. If you look at the first, at part A there, there'd be one normal vector coming out like this. Be another normal vector coming out like that, and another normal vector coming out like that. But all three of those would be coplanar to each other. They're all in the same plane. I guess the way I'm kind of imagining it is that they're all flat on the board for me. It's not perfect because I know the picture's angled a little bit so you can see it. One of the better ways for you to probably try and imagine it is if you do have your textbook handy, try this one. And you may need a partner because you have to hold a lot. But if you take your textbook and you have a plane there, how would I do it? You don't even need to open that. Pretend this part isn't here, okay? Make that the spine, and that the spine of your book, okay? And then make this part a page that you open up to, okay? So you've opened up your textbook like that. And then take three pencils and arrange those pencils. So one's going like this, and one like that. And I think it'll be more obvious to see there that those are all they're all in the same plane. And it's actually true for these ones here too. Right? If I was able to put normal vectors on all of those cases, the normal vectors would all be in the same plane. The only time that they're not in the same plane is if the three planes intersect at a point. So what that gives us then is this test for a unique point of intersection. So if we know the three normal vectors, we can check to see if the normal vectors are coplanar. So this is now the third time we've done this calculation. It's the cross product, then a dot product. We did it before as a test for coplanar vectors. And then we looked at it and we said, oh, it's also the way to calculate the volume of our parallelepiped. And now we're just using it as an application to see if three planes have a unique point of intersection. So if it turns out that we do the cross product and then the dot product, if we get any answer other than 0, then there is a single point of intersection. Okay, you'd have a single point of intersection. Now, keep in mind, that's not telling you what the intersection is. It's just a way of testing to see if there is one or not. Okay, worth noticing, but not the type of question that we'll be doing more often than not. I think it's going to show up in your textbook and the homework though. These are the big ones here. Determine the point of intersection of the plane. And I'm giving this one away. I'm saying find the point of intersection. So this one does have a point. I won't always tell you that. Well, I'm probably never going to tell you that from now on, because I don't want to give away the game, right? It could be one of several of those different situations, and we have to take a look and figure out what it is. The process would be, though, at least to start, look at those three equations and decide if any of the planes are parallel to each other or the same. And that should take you about 2 seconds to realize that they're not. Right? None of those are the same. So what we have to do, we're going to be trying to solve for x, y, and z. Explicitly, we're going to get to a point where it's x is a number, y is a number, z is a number. And we should be able to do that this time because now we have 3 variables, but we have 3 equations. Whereas in the examples we did yesterday or last class, there were 3 variables and only 2 equations. So this time it should work. It means we solve them a little bit differently. What we did last day was we eliminated one variable and then we eliminated a different variable. Well, this time what we're going to try and do is we're going to pair up equations and we're going to eliminate the same variable 2 different times. So I'll show you what I mean. I'm going to take the first plane and the second plane, x plus 2y. And if you look at these two, I want to eliminate one of the variables. And it's set up really nicely to do that if I want to eliminate the z's. So if I eliminate the z's, I'm just going to subtract these equations. It'll give us minus x plus 3y equals 7. Okay, and I'm going to call this equation 4. So I've kind of got equation 1, equation 2, and equation 3 already. I've now created a new one, and it's called equation 4. And it has just x's and y's in it. I've managed to get rid of the z's. So now the next part is I'm going to pick a different 2 equations, but try and eliminate the z again. So I've already used equation 1 and equation 2. This time I'm going to try using equation 1 and equation 3. And I could have picked either way. I could have done I could have done 2 and 3. That would have worked too. Just I picked one. And I still want to eliminate the z's. So if I want to eliminate the z's for equation 1 and equation 3, I'm going to have to multiply the first equation by 2. So that'll give me this, 2x, 4y. This is the part where I usually make a mistake, so I'm feeling a little nervous. And then equation 3 stays the same, 3x. And we're trying to eliminate the z's, so this time we should be adding them. So we get 5x plus 5y equals 25. And now we have that new equation. Now that one will simplify a little bit. 5, 5, and 25, I'm just going to divide everything by 5, just to make my numbers a little bit better. And I'm now going to call that equation 5. Right? So I've got equation 1, 2, 3, 4, and 5 now. But the advantage is, I'm going to pull equation 4 over, minus x plus 3y equals 7, and equation 5, x plus y equals 5. What I started with was 3 equations and 3 variables, and now I'm down to a situation where I have 2 equations and 2 variables, and that's now a grade 10 problem. Right? Now we can just solve this by elimination, and in fact this one worked out really nicely, more nicely than they usually will, because I don't have to multiply any of these equations by anything. If I just add again, the x's are going to go. I got 4y equals 12, and so y equals 3. So finally I've got to a point now where I have a value for one of the variables. I know that y is equal to 3. Now that I know y is 3, I want to sub that back into some of our previous equations. So I think if I take equation 5 there, it's probably the easiest one, and I sub in y equals 3, then I get that x is equal to 2. So now I've got both x equals 2 and y equals 3. I need to find z. Well, maybe I'll sub those into number 1. I could sub it into any one if I want. I could sub it into any one of the equations that I had. I'm picking one because I thought it was the easiest. 2 plus, and what's that? 2, 8, that is 4. So my point of intersection is 2, 3, 4. Okay. That's sort of our number one case. That's what we're hoping for, is that we're going to end up in a situation where all of the planes intersect in a single point. So what we did was we picked 2 planes, eliminated a variable, then picked 2 different planes, eliminate the same variable. That's going to create 2 equations with just 2 variables and solve from there. Okay, determine the intersection of the planes, if any. And I haven't told you what's going to happen. I don't know on this one. But we try it the same way. First look, and are any of the planes parallel to each other? Obviously not. So we can go from there. That means then that we want to try and eliminate some variables. And if you look, I think it's set up really nicely to just eliminate the y's. So I'm going to take equation 1 and equation 2. And we'll have to add these guys together. 4x. And that's what we get if we add them. If you can here, pause the video and see if you can work ahead. This would be a good time to do it if you can. And I don't know, maybe I'll grab 2 and 3 this time just to be different. 3x. Add these as well. So I get 8x plus 10z equals -1. Oh, and I forgot to label them, didn't I? This is equation 4, and this is equation 5. Okay, so I've got this. And I'd really like to eliminate a variable. They're not lined up as well this time, so maybe I'll multiply this equation by 2 so that my x's will cancel. And I don't need to multiply this one by anything. This becomes 8x and z. Hopefully you guys are already seeing a little bit of what's going to happen. Remember, I'm trying to get rid of the x's, but if I subtract these equations, I get a 0, x, a 0, z, and I'm subtracting, right? So that becomes a 7. So 0x plus 0z equals 7. Is that possible? No, we can't possibly have that. So we say there's no solutions. There's no solutions to this system. That means there's no common intersection. So it's not a point of intersection. It's also not a line of intersection. It's some situation where all 3 of the planes didn't intersect. Okay. But the other thing we know is that none of the planes were parallel to each other. So I'm going to back up for a minute to the start here. These were situations, this guy had no intersections, right? But all 3 planes were parallel, and that's clearly not the situation we're in. This one had no common intersection, but those planes are parallel, so we're not in either of those 2 situations. This one had no common intersection, but 2 of the planes were parallel, and we don't have that. This one had an intersection, so it's not bad. This guy had a point of intersection. This one had a line of intersection. This one right here has no parallel planes, but it also doesn't have a point of intersection. And so that's the situation that we're in. So there's no solutions because these planes, remember we said they intersected in pairs. And that's our conclusion for this. We're done after we say that. So it's not enough to just say that there's no intersection. we have to say that they intersect in pairs. We have to give an explanation for it. Okay, last one. So you can maybe guess what's going to happen. Determine the intersection of the planes, if any. What's kind of neat about this one, the third plane doesn't have a z in it, right? And that's okay. It just means the z component of the normal vector is 0. So that's all right. It's actually really good for us because equation 3 already doesn't have a z. So if I just take the first two equations and eliminate z, I'll create another equation with x's and y's, and we can just use it directly with number 3. So a bit of a shortcut, but I got to multiply by 7 to make it work. That'll give us a 14z and a 14z. And they're both positive, so I need to subtract. We have 4x plus 8y. Z's are gone. Equals minus 20. And you'll notice I could divide all of those by 4. So x plus 2y equals minus 5. That's equation 4. Right? That's the new one I've created. So this equation here and this equation here just have x's and y's. So if I put them together, sorry, you probably already see what's going to happen again, right? Just write it down so it's there. If we try and eliminate them, we'd subtract, we get 0x, 0y equals 0. And that's very different than the last case we had. Right? In that last one, we got 0 equals, I can't remember, it was some number. This time it's 0 equals 0. That means there are infinite solutions. And of course, I forgot to mention it because I was trying to hurry. But if we looked, and we should have at the beginning, none of those planes are parallel. So we don't have planes on top of planes. If we have infinite solutions, that means they intersect in a line. Which means that we have to find the line. We need to know where that line is. And remember what we did last day was we were trying to find equations of lines, right? And to do that, we knew that we needed to get a parameter in there. Somehow we had to let p appear. And we're going to do the same thing here. I'm going to just use one of these equations that we just had. So the x plus 2y equals minus 5. And all you do, you only do this if we've come to the conclusion that they're going to intersect in a line. Okay, it's the only time we do this. We're going to let one of the variables represent our parameter. So I'm going to say let y equal t. I have to let one of the variables equal the parameter. When I do that, that means x plus 2t equals minus 5. And so x equals minus 5 minus 2t. So now I've written x in terms of t, and I've also written y in terms of t. By the way, I could have gone the other way, right? I could have said let x equal t, but if I had done that, if you play around with it, I'll have to divide by 2, which would have made a fraction. So there was a reason why I picked y. I still need z. Right? I have x in terms of t, and I have y in terms of t. I also need z in terms of t. So if I come back up and grab equation number 1, it was x plus y plus 2z equals minus 2. And I'm going to sub in the value for y and the value for x with their parameters. So x is now minus 5 minus 2t. Y is just t. And there's our z. And if we start collecting some terms there, minus 5 plus t. Oh, not plus t. I made a mistake that time and caught it quick. Minus 5 minus t plus 2z equals minus 2. Just trying to get the z by itself, right? Divide both sides by 2. And there's our z value. So now I've got the line. Therefore, the line of intersection is x was equal to, where did it go? Minus 5, minus 2t. Y was equal to just t, that was only a letter parameter, and z is 3 over 2. So we've got a line of intersection. It's got a point and a direction vector. That's what we needed. Okay, so tough little question there. And again, you only introduce that parameter if we've already gotten to a point where we've determined that there's an infinite number of solutions. Okay, so don't do that. Don't put the parameter in unless you've got to that point right there. That's when you know you need a parameter.